Thank you. Thank you so much, Anisha, for that wonderful introduction. And I'm really honored to give this talk, especially to the WIDS community. And so, I'm really pleased and thank you very much for that. So I'm going to share my screen. So hopefully it'll work. Okay, so my talk is going to be integrating artificial intelligence, and by that I mean AI, ML, machine learning, data science, all put together, and cybersecurity. And in particular, the application we are working on for the US DOT is on transportation systems. So this is a $20 million program called Tracer over 5 years. And Clemson University is leading this effort. And UT Dallas is a principal member of the team. And Tracer stands for Transportation Systems, Cybersecurity, and Resiliency. So, and again, thank you again for, I'm really honored to give this talk. So I've got 3 parts. One is integrating cybersecurity, AI, ML, data science. So this is going to be sort of a very general topic in the sense, not with any specific applications in mind. Second, part 2, I will discuss security and privacy for Internet of Transportation and infrastructures. And part 3 is essentially our current work for the Department of Transportation. We started this work in January, and so we are just 2 months into it, January 1st or 15th, around that time. So just around 2 months. So I'll talk about sort of the directions that we are taking. And a number of sponsors, US DOT, NSF, Army, Air Force, NASA, NIST, and so on, NSA. And some colleagues I'd like to thank, Professor Alvaro Cardenas for Transportation System, Murat Kantajalu for data science, ML for cybersecurity, for securing data science, Latifa Khan for data science, ML for cybersecurity, and also our former PhD students, Raul Cunanes, and our project coordinator on the walls. Okay, first part is integrating cybersecurity, AI, ML, data science. So, in general, what is now this particular topic, trustworthy machine learning, and it's now more trustworthy AI. So, this is like one of the hottest topics now in cybersecurity. So, machine learning AI techniques that are secure, that means they have to handle cyber attacks, right? Machine learning techniques could be attacked. That's again a big challenge because we are applying machine learning for almost every application. Privacy preserving, meaning ensuring that one cannot deduce private information due to machine learning. Because in machine learning, you can put lots of stuff. You can dig and dig and dig and be able to extract data previously unknown. They have to be accurate, high integrity, and produce correct results. They have to be dependable, handling faults and recover from failures. And they have to be fair and unbiased, not discriminate against individuals. And now I'd like to add one more topic, which I haven't mentioned here, but something that we are just beginning to look at right now. We are hearing so much about large language models like ChatGPT. What's the implication? What are the security implications? How can we apply that for security? And how can we secure large language model-based systems like ChatGPT? So that's not part of this talk, maybe sometime in the future. So here is a diagram I took from one of my papers in IEEE Intelligent Systems. So I teach a class on trustworthy machine learning, not only at UT Dallas, but also University of Dishang in Cameroon, Africa. And so the way I do it is the infrastructure is cloud-based. Eventually, I think it could be quantum-based. So I'm not there yet. Then we have a data management, big data management layer, like HBase, Hive, and so on, and it has to be secure. Then machine learning, we look at various machine learning techniques. And then the application we apply to cybersecurity, social media, IoT. It could also be domain applications like healthcare and finance. Sorry about that. And the left-hand side, we have security, privacy, integrity, availability. And then, of course, we also need fairness, unbiased, anti-discrimination, and so on. So this is sort of the complete picture of trustworthy machine learning. So just to just to sort of have a reference point. So we are going to focus on what about not so much the fairness, that's our current work, but security and privacy aspects for machine learning, and then applied to transportation systems. Well, that's our application. Okay, so privacy-aware quantified self. So we are carrying, practically every one of us has got multiple mobile devices, right? Smartphones, such as, they are prevalent. Now, one thing, sociologists and psychologists have done some very interesting work on quantified self. And their goal is to analyze all the data about us and give us advice. And so, for instance, I really like milk chocolate and vanilla ice cream, but we know that that's bad for all of us, right? And so wouldn't it be great when I open the refrigerator and then my smartphone sort of pings or dings and says, no, you're not supposed to eat milk chocolates. Fortunately, I don't keep any milk chocolates at home, but, that could be a big problem. And so, but that would be very useful for me, right? Because it's going to give me advice and I would likely get healthier. But the problem we have is my privacy, because some malicious user could get all the information about me and send it to, my insurance company, health insurance and car insurance and whatnot. And so that's the thing. Retailers can use all these information using cloud-based services and so on. So such data collection sharing are often being carried out without the user's knowledge, right? So a lot of danger. So if they find like I've got diabetes or something, not only is it going to affect me, it's also going to affect my son and my grandchildren. So that's, quite dangerous, because who knows, that could be a policy in the future that if one of your grandparents has had diabetes, then, you have to declare it and we may have to reconsider your insurance. So such privacy violations could get out of control if you can combine some information with other previously known information, put it all together. So to address these growing challenges, what we need, yes, we do need quantified self, but we also need these applications to be secure and they have to enforce privacy. Okay, so this is what we have designed and developed. Privacy-aware, policy-based quantified self data management framework. So in our little smartphone, we have data collection, data storage, data analytics, data sharing, and so on. Okay, so what is so unique about this? So we get health information, fitness, location, social media, all kinds of data about us to give us advice. So, but what we are saying is, and we are working with a sociologist on this, whatever we gather, data collection, policies have to govern. And when I say policies, we computer scientists, we use TOY policies. But by working with policy experts, we are getting some better understanding. So I was very frustrated that all our policies were like, I share with like little children, right? John shares with Mary, provided Mary doesn't share with Peter. So, and I even took a certificate about 3 years ago, the London School of Economics on public policy. But even that didn't help, because you can't just get superficial certificates and expect to be a policy expert. So we are working with our Dean of Policy Sciences, Dr. Holmes. So policies have to govern data collection. What does that mean? How long are we going to keep the data? 30 days? And what purpose are we collecting? Do this experiment. After that, are we going to delete? And what does it mean to delete? What accountability? Because data is not like jewelry, where you can go to the bank and remove your jewelry from the bank box, right? So how do you delete? What about accountability? What about auditability? And then data storage and access. What are the policies for storage? For data analytics, what are the policies for analytics, right? You don't want to give out the raw data, but you might be able to share your machine learning models. So, and then of course, data sharing, right? Sharing data is so important between your doctors and insurance companies and your hospitals. And, I've had some personal experiences in my family where, data sharing really helped the situation. Okay. So again, what do we mean very briefly this slide, because I don't want to waste too much time on this. I've already talked about many things here. So this is our mobile app that we have developed. And then, you use, oh, by the way, you use some of the data in the cloud because you can't store everything here. And they could be encrypted and access the cloud through cloud-based services. And that's what we are showing here. So what would be ideal is to keep all the data encrypted and then work with encrypted data. Yes, theoretically it is possible with homomorphic encryption, but practically it's not. And hopefully when quantum computing becomes really real, then we might be able to, solve some of these problems, but that raises a big danger because quantum computing can break almost all the codes in milliseconds. So we have this post-quantum cryptography. So I'm not getting into this, but one thing I tell all my students, including myself, right? We really, in the future, we have to learn some or other not become experts, but at least some handle on quantum computing. So I tell them the areas are quantum, AI, data science, machine learning, or AI machine learning, cybersecurity, blockchain, and then data science. We can, integrate data with AI or have it separate. This doesn't come from me. It came from the NSF assistant director in one of the workshops that we participated. Anyway, so this is the policy-aware data collection, a lot of data being collected based on access control policies. Some applications, are run locally, some we can access through encrypted data through cloud-based services. And the question is, do we need to collect lots of data, right? So, for example, when you want to weigh yourself, if you're 20 years old, you may not want to weigh that person every day. Even if that person has a huge dinner and puts on 5 pounds, it's not going to be a big deal. But for a 8-year-old person, having a huge dinner, putting on all this weight overnight could be taxing on the heart. So that's why we have to decide, and policies have to govern that. So again, data could be deleted, but what does it mean to delete the data? We envision that data sharing analytics will be carried out using the services. And based on different scenarios, you can encrypt some data and you can sanitize some data and so on. Okay, so this is a system we designed and developed. Now I'm moving on to the second topic because these are our key topics that we have conducted extensive research integrating cybersecurity and machine learning. So second is applying, I said, data science or machine learning for cybersecurity applications with big data stream. So again, we use past data to build classification model, predict labels for future instances using the model, helps decision making. You might ask a question. We've been doing that for 30 years. I remember I got into data mining, I believe in around 1992, 93. And we were developing data mining for some of our customers when I was at MITRE Corporation as early as 1995. And this is what we did, But the difference, even when I was at NSF from 2001 to 2004, it was a challenge. We only built one model. So what happens if yesterday it's by Microsoft, day before yesterday, say by Facebook, today by Google, tomorrow maybe Amazon. So the models, the concepts are changing, the concept drift. Concepts are continuously changing. One model by Microsoft is not going to help us. So we have, and that's the unique research here. Use past data to build classification model, predict the labels of future instances, using the model help decision making. But big data means continuous flow of data, very common in our connected world, massive amounts of data. So what we are doing here is so we are looking at network traffic data because it's cybersecurity data, but you can think of it as stock market data, continuously arriving. And we are breaking the data into chunks, and then we are building not one model, an ensemble of models. Now, this model, right, would be outdated. So we throw it away because we can't have an infinite number of models. So we throw it away, and then we work with the rest of the model. With the remaining models that we have built, right? So how do we throw this away? The models we have an algorithm. Models talk to each other and decide which model is not accurate. So sometimes there could be a human in the loop to update the models. Then, of course, the So the training and testing time, attack traffic, we block and quarantine, and benign traffic, we store. So that part doesn't change. But again, the challenge is building the right set of models. And we applied it to a number of applications, one being insider threat. And I'm going to skip this chart. This is very briefly. Insider threat means bad people, right, pretending to be good in an organization. And we have heard over the years about espionage. We had a person called Ames in the early 90s who was giving secrets to, about US secrets. He was working for the CIA. That's an insider threat. And in the early 2000s, we had Hansen from the FBI, also an insider threat. They were giving US secrets. So similar to that, even the bad processes planted by hackers pretend to be good. They could be like part of a database, part of an application, part of, they look like normal processes. So again, what we did was the stream, ensemble-based stream techniques, right? We have applied it to handle these insiders who may themselves be evolving, changing their behaviors, changing their patterns. So it's not one type of insider. And so we use traditional support vector machines for supervised learning. And then we also use unsupervised learning, compression-based techniques for unsupervised learning, combine both, right? And unsupervised actually gave us some good results. So this is our architecture. And again, the user is typing, various system calls and so on, and features are extracted. And then we are dividing the data into chunks. So we have I chunks, right? And then extracting features, we are applying supervised, unsupervised algorithms. And main thing is building an ensemble of models where sometimes we have to throw away models from periodically when they are outdated. When the K+1 chunk arrives, then of course we test. And then it's going to tell us it's an anomaly or not, okay? So actually, we initially started this this line of direction, our work for NASA, right? And now we are applying it to sort of cybersecurity problems. NASA to detect faults in the spacecraft. Okay, so now we come to the most important, as I said, one of the most important areas of cybersecurity, and that's adversarial machine learning. Adversary is learning about us, our models, our data, poison the data so that it's not going to get caught. So imagine machine learning is being applied for retail, for healthcare, for finance, for everything, right? Almost every application, even cybersecurity. What happens if these machine learning techniques are attacked? So adversary modifies data to defeat the algorithms. So we have to understand what the adversary is up to. It's not concept drift. It's not online learning. Adversary adapts to avoid being detected. So today I've got sort of black and gray hair. Tomorrow I'll come with blonde wig, and then maybe a red wig, whatever. So avoid being detected. It's not online learning. Adversary adapts to avoid being detected during training time, data poisoning, and so on. So in the end, it becomes game playing between us and the adversary. So look at this. The red squares are bad instances. Green circles or blue circles are good instances. And this is a support vector machine boundary line. Adversary is trying to send its data. There are bad instances, learn where the boundary line is, and pushing it down. So now 1, 2, 3, 4, 5 instances are going to be considered to be good instances. And that's really bad. Even if one bad instance comes in here, it could create a lot of problems. So what do? First of all, we have to study the attack model. And I'm not going to go into these equations. We just look at two models. One is free range, where we can, adversary can move the malicious data anywhere in the domain. And then the targeted attack, adversary moves malicious data closer to the target point. So our paper, KDD paper, explains a lot of the details. Okay, so what did we do now? We studied the adversary. How is the adversary going? So here I've reversed it in the sense that green circles are good, the red crosses are bad. And the dotted line, the dashed line, is the standard support vector machine. The yellow line I showed earlier. Now, adversary is studying, and look at this. Some adversary is trying to push some of these red crosses as good instances because it knows exactly where our line is. So we've got to be smarter. So we've got to learn what the adversary is, a lot of mathematical computations and applying game theory. And so what's happening here is that we are doing these calculations and moving the support vector machine to line a little higher, blue line. That's our new support vector machine. So now all of these black things are sort of the bad instances, just to separate from the red, okay? All these bad instances are now caught. Yes, some bad instances have escaped, but a lot of bad instances are caught. And now this blue line, you could ask the question, why not move the blue line right here? Then all the good instances will also be known as bad instances. So we don't want false positives and we don't want false negatives. So this is sort of the line of research that a lot of people are following. Now, some people, I was in a panel with about two years ago, and it was actually a panel virtual in Zoom in India, and there was this professor, very talented professor from University of Oxford. She does work in formal methods, and she's saying, like when I talked about the game theory and so on, eventually, how are you going to continue playing this game? We need to bring in formal methods. In the meantime, what we are doing here, so there are two parts to it, okay? First part, we are trying to do a lot of these algorithms, we're seeing whether we can do it in hardware. Intel came up with an SGX-enabled data analytics platform. And so now what we are doing is seeing where we can execute this highly critical machine learning algorithms. They have to be in protected memory enclaves. So there's something called SGX, the platform enclave memory, where all the machine learning algorithms are executed here, which is supposed to be secure. It's tamper-proof. So that's one way. I'm not saying this is the only way, and this way is correct. We need to, produce more results and analysis. But the lady from, so the TEE is Trusted Execution Environment. The professor from Oxford is saying formal methods for machine learning, including logics. She was talking about temporal logics, maybe what are the other logics for specification for deep learning, and the verification of the machine learning algorithms. So because of, I know machine learning was really big at one time, and then it sort of goes up and, not machine learning, formal methods. But now I think with these machine learning algorithms and AI to ensure that they are secure and safe, we may have to examine formal methods. Okay, so that finishes my part one. Part two is actually much shorter. So security and privacy for Internet of Transportation. This is what got me into transportation systems. My colleague Alvaro Cardenas, and that was about 7 years ago, where we had a joint student, Raul Quinones. And that's when I got into this particular area. So Internet of Things, we have the Internet of Home Things, right? So what does it mean? We have our microwave talking to our clocks, to our television, to our smartphones and tea maker, coffee maker, whatever. Internet of Transportation, we've got the cars talking to trains, to trucks, and so on. They're all communicating. And the biggest problem we have, one of the major challenges, security. What happens if all this communication, is attacked? And then what about the privacy, right? I may want to smoke in my car, or I might want to protect my location, but if my privacy is violated, they could take a photograph and send it to my insurance company, and then there goes my insurance. So, but again, smoking is dangerous, or drinking is even more dangerous when you are driving. But then, you also want to say, okay, I want to maintain my own level of privacy. So Internet of Transportation, we know that autonomous vehicles, and this is just very briefly, they improve traffic, transportation of goods, and so on. In the US, trucks carry 63.3% of the freight of goods. AV is not limited to ground vehicles. So we have looked at ground, aerial, and sea. And now, very recently, like last couple of weeks, we are looking at space, because apparently the next big thing is going to be space systems. So with a wide variety of applications, so level of automations range from 0 to 5. Current ground vehicles have lower automation, and aerial vehicles like airplanes and so on higher. Companies are interested heavily. GM spent $728 million in 2008, $1 billion in 2009. I haven't gotten the numbers after the pandemic. So there's a lot of great potential in AVs, we know that. And so security and privacy concerns, and I'll explain some. AVs emulate their environment, and they are using, AVs emulate their environment using a variety of sensors, right? There could be the cameras, global positioning systems, inertial measurements, and so on, LIDAR, radar, and ultrasonic sensors. Now, the question is, what sort of attacks are more prevalent, with these gadgets? So there's been quite a bit of research, including the work of Dr. Cardenas. So previous research has shown that sensors are susceptible to malicious tampering, and inertial measurement units are susceptible to sound waves, and global positioning systems are susceptible to spoofing. So these are some of the prior work. So again, the challenge that we have here, vehicles should verify the veracity of sensor signals before they act upon them. But the problem is, verify means, right, time. So these sensors are, again, such tiny gadgets. They don't have as much space. So we need some novel methods for security and verification, because the traditional methods may not work, right? Because we don't have enough space in those tiny sensor gadgets. And real time is important. So imagine bringing in real time and security and so on. So this is also one of the directions that we are pursuing for the Tracer project. The real time part and security is not really from the UT Dallas part, but see, we are about seven members, right? Purdue, UC Santa Cruz, and UT Dallas, and Morgan State, and University of Alabama. So everybody has got, so our responsibility is integrating AI and security and looking at privacy. Okay, so anyway, our first thing we did with it's actually published, this paper, okay? Physics-based anomaly detector. So to build a reference monitor using a physics-based anomaly detector, PBAD, algorithm. So reference monitor is that part of the system, right, that has to be secure. It has to be tamper-proof. This is what we study in Operating System Security 101. So, when I got into cybersecurity back in 1985 fall at Honeywell when I joined, the first thing they brought me was operating on my table, some books, Operating System Security, and first thing I learned was reference monitor. Anyway, but this reference monitor is not operating system reference monitor. So our algorithm has two parts: building a model offline of the physical invariance, implementing an online tool to monitor expected and observed behavior for anomalies, and if there is any difference, raise an alarm, right? Offline pre-processing, online verification, anomaly detection. Here again, your question, what is the big deal here? Right? You model the system, build this verification online, and then detect anomalies. The challenge is modeling the system. So Alvaro Cardenas, he's a control systems engineer and an expert in cyber physical systems. He's also a computer scientist. Now, I don't have, although I did some physics in my undergraduate, I don't have experience modeling these real world systems. So we were very fortunate that Alvaro was the faculty at that time. So he and Raul, they developed the model of the system, right? So the AV's invariants are calculated using well-known nonlinear models, accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis for the aerial vehicle positioning and steering. Angle is used for ground. Okay, we did for aerial and ground. And these are all the parameters. So once we have model, which is a challenge, then we can start applying, is it machine learning? So initially we said, let's look at Kalman filter. Control engineers, systems engineers, and electrical engineers, they have been using it for decades. So extended Kalman filter, it's used to predict the AV's physical behavior by estimating unknown parameters from now noisy sensor inputs, right? So we divide the algorithm into two parts, the prediction and then correct the estimation, and then we compare it against the sensor data. So for anomaly, so once we finish the online stage, the anomaly detection, we apply the CUSUM, a statistical algorithm, is used to detect the persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. So it's a reasonable method, but it's somewhat sort of a old style method in the sense we are not looking at this modern, deep learning and so on. But reasonably reliable method. Okay, so what were the results? So we did it for drones, which was our aerial, and then the vehicles. So for drones, we looked at aerial AV Intel ready to fly, controller PX4 flight controller. We focused on detecting GPS spoofing and gyroscope attacks. So the GPS attacks detected after 0.2 seconds, the gyroscope attacks after 1.5 seconds. Overhead was about 5.4, a little bit high. The ground, we used the Traxxas Ford Fiesta. Controller was ROS, Kinetic Aim, focusing on detecting visual attacks on the camera, attacks detected after 0.1 seconds. So the overall overhead was about 2.25, and accuracy, each threshold produces a probability of false alarms of 2%. Now, today, 2% is still not good. We should have it like 0.000002%. Now, 10 years ago, or 15 years ago, I talked about some other problem, and I was saying we had about, about, I don't know, 10% false alarms or false positives, false negatives. And these people said 10% is just absolutely horrible. You need to bring it down to about 1-2%. But now 1-2% is not good, right? We have to really bring it down. Okay, so maybe the AI techniques. So now, what about privacy? Now we are doing work on privacy, but at that time, for our tracer project, but before that, we did not do work on privacy, but we felt that it was important, right? Beyond the security of individual vehicles, transportation sector could greatly benefit the supporting infrastructure where, what we really need is communication between vehicles, motion sensors, lampposts, and so on to help identify traffic jams, reroute the vehicles, increase vehicle safety, and so on. Now, from the user's perspective, right, privacy concerns arise from all the information needed by such systems. So a lot of information is being collected, that could lead to private information being exposed, such as vehicle identification and driving patterns, right? So I really don't want anyone to figure out what my driving patterns are, because I've been given tickets not for driving fast, because I've got this tendency to drive too slowly. And when you try, I don't know, in Texas, when you drive slowly, they give you tickets. So I'm really careful now. And legislatures, engineers, scientists should keep privacy in mind, because if I know that, that some level of privacy is provided by these systems, then I will be using, the adoption rate could be much higher. Otherwise, I may not adopt these technologies, right? So that's where we are. But now, this is what we are doing for our current tracer project. So we talked about AI security in general for various applications, and then transportation system where we took a very traditional approach. And now, under the tracer project by the U.S. Department of Transportation, how do you bring in AI and security for Internet of Transportation? So I'm just going to provide a summary. On December 12th, I gave a really 1-hour talk for the U.S. DOT for this tracer, where all of the transportation systems, they have transportation systems for different areas. So for, one is for reliability, and there are like 5-6, this is national transportation centers. So our focus is the only security transportation center. So I gave this presentation for the US DOT. But we are still in the beginning stages, and I've summarized it. So AI for transportation security, right? Data science AI. Internet of Transportation subject to attack. We use Kalman filter. A lot of streaming data, sensor data being collected. And again, when they go electric, we also need energy conservation. So threats to security of such systems could cause massive damage, including accidents, loss of lives, and so on, right? And attacks to energy management center. So data science ML techniques are being applied to analyze the data. That's what we did earlier. Now the question is, can we apply what we have done for financial systems and telecom systems and network data? for transportation data. So what I'm doing now, actually, I should have produced a report last night, but I've got a 2-day extension for tomorrow, is looking at our particular application we are focusing on is transit systems, right? Transit systems and transit security. Transit systems could be anything, tubes and underground, and also it could be Uber, various transit systems, but they are all sort of connected through some kind of a management center. So I'm looking at every component of this transmit system, and in terms of CIA, confidentiality, integrity, and availability, how are each of these components being impacted? Okay, so that's an exercise I'm doing, and hopefully others in our team. So we've got some hardcore research that we are doing, but we are also building this next generation platform for transportation systems. So we are in the beginning process for that. And again, we are looking at the transit system aspect. So there are two parts to this project. Anyway, the main question is to understand the nature of the complex transportation data and adapt the stream analytics. So for instance, how do we understand? So before I started the Tracer project, when I was doing the research on just transportation systems, I didn't really have a very good understanding. But now that I understand what this transportation systems, the architecture looks like, and again, we are focusing on this one particular subsystem, which is a transit system. And within that subsystem, there are many components. Okay, so we are taking component by component and doing an analysis. And of course, the integration of all these components also have to be secure for that one particular subsystem. And so that's where we are here. Okay. Then for adversarial machine learning, this is something Dr. Murat is doing currently with Alvaro. So I haven't really done a lot here now at this time for transportation systems, but just monitoring what they are doing. So again, Internet of Transportation will depend heavily on AI, ML. Adversary will be learning the models used by the vehicles, right? Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing, just like what I said earlier. Challenge is what sort of game? Are they looking at zero-sum, Bayesian, Stackelberg? So we have to understand the data. And research on this topic is only beginning, meaning for transportation systems. So Murat and Alvaro have already started this work. And so in my presentation in December, I talked about some of their early work in this area. And so I'm really looking forward to seeing how they can apply remember the adversarial models I mentioned earlier, right? And how can they take that technology or those algorithms and applying it to transportation systems? And that is exactly what they are doing now. Then for privacy, this is sort of my direction. So I'm a little bit involved in their privacy project. And so privacy-aware policy-based. Remember I showed about our smartphone, getting all kinds of data, healthcare data, social media data. So now in the car, there is this little gadget and collecting the radar, GPS cameras, LIDAR, ultrasonic sensor data. And some data could go into cloud. So the whole infrastructure, when you look at the transportation infrastructure, there is some things that go into the cloud for analytics, right? For long-term analytics in the IoT environment. So what we are saying is policies have to drive. Now, fortunately for us, right, University of Alabama has got, so every university has got different, coming with different strengths. University of Alabama is, quite well known in the policy area as well as some of the risk aspects. So all of this data being collected, what does it mean data collected, right? Can you tell wherever you're collecting the data, I'm only collecting it for 10 days. So whereas for healthcare data, it's different, right? We will be able to, there are already fairly established policies. How long can you keep the data that you collect? So here we are coming into some new challenges about what are these policies. Data collection, data storage, data analytics, data sharing. All of this is happening inside the vehicle. Okay, so that's what we envisage. And so we have these research projects, right, like privacy, and we have a research project on adversarial learning. But then we also have what we call the foundational project. We are building the next generation of secure transportation system. Okay, so that's more an experimentation project. And then my one before the last slide, developments in integrated cybersecurity AI, it's exploding. So we looked at AI for insider threat and security for AI. That's sort of the most, data science, AI, ML for cybersecurity. I mean, that we've been doing it for 30 years. But the challenge now is adapting, right? Adapting meaning the outcomes are changing. The concepts are drifting, right? By Microsoft, tomorrow by Facebook. So we've got to adapt. But these AI techniques could be attacked. And now we are sort of applying this, as I mentioned, under our Tracer project for transportation systems. So privacy, healthcare, managing one's life's activities. And I talked about privacy-aware quantified self. And that was our work. Whatever I talked in part 1 and part 2, that work was mostly done before the pandemic. Part 3 is what we are doing now. So at the same time, with the development of IoT and transportation systems, security and privacy solutions are being developed, right? So we talked about physics-based systems. But driverless cars become reality. We have to rely heavily on ML. How can we develop AI solutions to detect malware in AV systems? And that's something my colleague Latifah Khan is focusing on. How can we develop a privacy-aware policy-based framework for Internet of Transportation? That's sort of my interest. And then we are also looking at attacks, adversarial ML. Okay, that's also some current work now. But something that we haven't looked at here, and this is what Adlani was saying from Oxford, are formal methods a solution for trustworthy machine learning? Or should we do this in hardware, right? The question is, all the research that we are doing, especially adversarial machine learning research, is it really going to produce reasonable results? So that is something that we are thinking. And we are very active in this now. What about fairness of the algorithms, right? We've got some of the basic research. My colleague Latifah, he's doing some basic research on a project from NSF, but looking at that research, he's applying it to the fairness now to transportation systems. So example, for transportation system, we don't want the police, right, to always stop people of a particular ethnic origin, right? So there are a number of sort of fairness-based problems that we have listed, my colleagues have listed. So this is one, right? Police stopping people. And also for speeding, right? If they see that it's a, person from a particular ethnic origin or gender, they might be stopped for speeding. But another thing that when we wrote the proposal, we didn't even think about it because at that time we were not talking about LLMs and ChatGPT. It all happened a year ago. So how can LLMs be applied for transportation system security? Can they help us with security? But what happens if LLMs themselves are attacked? Okay, so in general, we need to, before we get into transportation systems, we have to look at how can LLMs be applied to help us for security research? Can it help us with cyber attacks? We put in all the information and then can it say what are the type of attacks in the system? And what if these LLMs are given some garbage data and these LLMs are attacked and giving us all kinds of incorrect information? So there are two aspects to it. But what I'm saying is there is numerous opportunities, right? I mean, this 45-minute talk, exactly 45 minutes now, and numerous opportunities that we have for lots of research, like from what I have said, talked about today. So that is the end of the presentation. I'd like to thank, again, USDOT for us to be able to continue under the National University Technology Center, of course, Clemson University, and the director, Professor Mashur Chowdhury, for his leadership and including us, our Tracer team members, and at UT Dallas, Dr. Kantajulu and Dr. Khan. We work very closely. And Alvaro Cardenas was here with us, and now he's at UC Santa Cruz at a two-body problem, so he's there now. And we still work closely with him. And he got me into transportation system in 2017, co-advising Dr. Raul Quinones. And then Ms. Rhonda Walls, our project coordinator, and we have a very strong cybersecurity team. And again, thank you very much for inviting me. I'll open the floor to questions if you have any.
I can ask a clarification question.
Yeah, sure.
In the final slides and also towards the beginning, you had talked about privacy in an individual, both as an individualistic way to prevent association between a data and its membership. Is that how you're considering privacy?
That's actually a very good question. In general, when we talk about privacy, right, it's about individual privacy, right? My private information about my healthcare details, my driving patterns should not be divulged. But remember, I have come to work on privacy from a completely different environment. When I was at MITRE and Honeywell, I was doing something called inference problem for the military. Okay. And so there you put unclassified pieces of information together and infer something that is top secret. Okay.
Yes.
But the general privacy, those who are working directly in privacy don't consider that. But I also look at both aspects of privacy, because the second one that I mentioned, you can have a lot of private pieces of data together and put it together and infer something that is highly, lot of public pieces of data together and infer something that is highly private. So to apply some of the inference work I've done, we can handle some of the solutions there. But most people in data privacy who started this whole work of privacy preserving data mining after 2000 are focusing on individual data privacy. I hope that answers your question.
Yes, it does. Thank you.
Yeah, you're right. It's very confusing for someone. It could be confusing to someone who hasn't had that background in the early work, you see. Thanks. Any other questions? Could I ask a question, Anisha? So what work are you all doing in the sense on security, privacy, and AI? Are you all sort of doing some work on integrating these systems? I'm just interested.
But
Is there anyone who's working on security in machine learning integration? I don't think anyone in the room is working on similar topics, but I can share more information. Yeah, please. I'll be very interested to find out more. Yeah, because actually the one of even NSA now, they want to start with because I think we have worked with various agencies on the Ensure project, but cybersecurity. The agencies give us like federal labs give us problems, and then we work on research problems. But in any case, that's for our CAE, CAER, right? Cybersecurity research education. Now it's good. They are going to start we are going to have some beginning discussions in April. They're going to start a new effort where have CAE, CAER, everything in AI and security integrated. So when you say AI and security, it's not just what I talked about. I'm more bent more towards the machine learning. So for me, AI, well, I came from expert systems. So when I was at Honeywell, I developed an expert system for control system. Nobody talks about expert system anymore. That's just so archaic. But machine learning has become like AI for me. But now they are looking at much broader, which means including LLMs and then incorporating security. So how can you build an education program in that? And in addition, NSF is starting a new scholarship service, like a pilot. There are discussions on AI, only AI. We've been having security scholarship for service now for 25 years. But now they are going to start AI. So I think AI is, whether we like it or not, it's here and it's going to be here. And so what I feel is security, take advantage of AI for security and make sure that AI is fair and balanced and has got, and it's also secure. So I just wanted to mention that. It's absolutely, it's a critical security in machine learning. Yeah.
study is definitely a critical topic. And I'm pretty sure there are teams and we're working on it to set kids in trouble. So
And also, Anisha, yeah, bringing this into LLMs. I mean, that's something my colleague Latifa is looking at, and I haven't started because I'm teaching blockchain. So, and obviously, right now is first time we're teaching blockchain. So I'm spending a lot of time on that. As soon as I finish, I really want to get into LLMs and security.
yeah. On that note, I do want to express that the number of topics that you've covered, the range of your involvement in the range of topics is definitely commendable. The ranging from mobile applications to physics-based machine learning models and that is integrating them with control and stuff. Fascinating. So thank you again for joining us today and sharing your insights on all the subjects.